Hello everyone. In this class, we are going to discuss about the signal flow graph in systems and their representation of control systems. So let's recall what is an input and output and definition of transfer function. So what is an input? An input is the signal applied to a system. What is an output? An output is the system's response. And what is the transfer function? If we come to the transfer function, the input is represented as R of S and output is represented as Y of S and the gain as G of S. So we can define the transfer function as it is the ratio of output to input in the Laplace domain assuming zero initial conditions. And today's topics for discussion is why signal flow graph, introduction of signal flow graph, elements of signal flow graph, and purpose and applications of signal flow graph. So now when systems are simple, we use block diagram representation, but when systems becomes complicated with multiple feedback loops, interconnected subsystems, we can use a block diagram reduction technique. Means it becomes lengthy and confusing. So this is where signal flow graph becomes very powerful. So why signal flow graph means block diagram reduction requires rearranging blocks again and again. But signal flow graph provides a systematic representation, a direct mathematical approach, no need for repeated rearrangement. It simplifies the analysis of complex systems, especially when multiple loops are involved. So this shows the block diagram. R is input, C is an output, and gain and feedback loops are available. But if we use a signal flow graph, means we use nodes and forward paths and loops are available. So next one is introduction to signal flow graph. It is a DT empathize and defining part. A signal flow graph is represented as SFG. It is a graphical representation of a set of linear equations. So now let us see the SFG terms representation. So in this diagram, the x1, x2 and x3 is available. The x1 node represents the input node and it will act as a source node. And the arrow with the branch point is represented as a branch. And the value of A is represented as a transmittance value. And the x2 is a mixed node because it has a source node and the output node. And this is a loop point because it is starting point and ending point of this circle is ended with the same point. So we called it as a loop. And it is a mixed node. It is the another input source node is available and it represents the mixed node is x3 and the output is also x31. Now let us deeply discuss about the nodes, branches and everything. So the elements of signal flow graph, the first one is nodes. That is, nodes represents a system variables. There are two different types of nodes, that is input node and output node and intermediate node. Each node represents a variable such as x1 of s, x2 of s or y of s. Let's come to the branches. So branches represent functional relationship between the nodes. So a branch has a direction and has a gain. The gain represents multiplication by a transfer function. For example, if x2 is equal to g of s into x1. So then we draw the branch from x1 to x2 with gain g of s. And third important element is path. A path is a continuous sequence of branches from one node to another without passing through any node more than once. The gain of a path is the product of all branch gains along that path. Next one is a forward path. A forward path is a path from the input node to the output node without revisiting any node. The total gain of the forward path is calculated by multiplying all gains along the path. Next one is a loop. A loop is a closed path that starts and ends at the same node. The loop gain is the product of gains around that closed loop. Non-touching loops. The two loops are non-touching if they do not share any common node. This concept is very important when applying Mason's gain formula. Now let us move to the formulas or rules of elements of signal flow graph. This is the defining part of the DT. The rule 1 is incoming signal to a node through a branch is given by the product of a signal at previous node and the gain of the branch. So let's example x1 is input node and x2 is output node. The output is x2 is equal to, we can write a into x1. And if we consider x1, x2 with a1 and a2 inputs, we can write x3 is equal to a1 x1 plus a2 x2. Rule 2 is cascaded branches can be combined to give a single branch whose transmittance is equal to the product of individual branch transmittance. So x1 is equal to x2. The x2 input is x1 into a, but x3 output is x1a, x2b. For replacing x2, x1a, we can get x1 into ab. So here we can simply write x1ab into x3. Rule 3. Parallel branches may be represented by single branch whose transmittance is the sum of individual branch transmittance. The branch transmittance A, B. So sum of transmittance is A plus B. So we can write x1 A plus B x2. Rule 4. A mixed node can be eliminated by multiplying the transmittance of outgoing branch to the transmittance of all incoming branches to the mixed node. So x1a plus x2b equal into c equal to x4. So we can simply write x1ac, x2bc. So x4 is equal to x1ac plus x2bc. Rule 5. A loop may be eliminated by writing equations at the input and output node and rearranging the equations to find the ratio of output to input. This ratio gives the gain of resultant branch. So we can write x1 ab by 1 minus bc. We can write b by 1 minus bc. We can multiply with the branch value ab by 1 minus bc. This is the proof of this rule. Mason's gain formula. The overall gain T is equal to 1 by del summation k pk del k. T is the transfer function of the system. Pk is the forward path gain of kth forward path. K number of forward paths in the signal flow graph. Del is the 1 minus sum of individual loop gains plus sum of gain products of all possible combination of two non-touching loops, and this is 3 non-touching loops and etc. Del k equal to del for the part of the graph which is not touching kth forward path. This is an exercise for the signal flow graph. Let's summarize the signal flow graph session. So we can analyze the input and output transfer functions, why we require a signal flow graph compared to block diagram reduction techniques, and the rules of signal flow graph with n examples, and the applications of signal flow graph. Thank you.